In this video, I want to do a quick example of confidence intervals and then start moving towards what's called the T-statistic. 64% of a simple random sample of 550 people leaving a shopping mall claim to have spent at least $25. Determine a 99% confidence interval estimate for the proportion of all shopping mall customers who spend over $25. So we've got a confidence interval, so please remember the steps here. State, plan, do, and conclude. And many things here, the hardest portion is the state and the conclude. The math is more the plan and do, and that is not so tough to do. All right, our state, build a 99% confidence interval for the proportion of all customers at the shopping mall who spend over $25. Okay, let's do the plan. Well, we had a simple random sample, so that's good. I guess I should also say we're building a proportion interval. We kind of take that for granted right now because we only know how to do the one, but pretty soon we'll know more intervals. So we had a simple random sample. Of course, we were going to think that 550 people is less than 1/10 all shoppers at the mall. And so that's kind of our first condition. And remember, the second condition is 550 multiplied by 0.64 and 550 multiplied by 1 minus 0.64. This first thing is 352. That's greater than or equal to 10. And this other one is 198, which is bigger than 10. So we have fulfilled our conditions. So now we do. Okay, you're doing a one proportion Z interval. The one little thing of note here is, remember, we have to have the number of people. So that 352, 550 confidence, and we calculate. Okay, so here's our interval. So that would be our do. We'd write I'm just going to go to two decimals, 0.59 and 0.69. And then we conclude. Okay, so we are going to conclude. We are 99% confident that the interval from 0.59 to 0.69 captures the proportion of customers at the mall who spend at least $25. At a certain plant, batteries are being produced. A simple random sample of 50 batteries finds a mean life expectancy of 12.35 months with a standard deviation of 2.41. Find a 95% confidence interval for the life expectancy of all batteries being produced at the plant. Now, this is where we are going to make a leap from Z to what is called the T-statistic. And the reason is simple. It's the deviation. The deviation comes from not a population, but the sample. It is unrealistic to know the population standard deviation for a number of reasons. I mean, obviously, we would have to take a census of every battery being produced. That's an unrealistic thing. But the other piece of this that maybe lends itself to kind of this weird calculation is if we'd taken the population, they'd taken a census of every battery, then we would know the mean. We would have calculated it. So why would we build a confidence interval? So since the 2.41 came from a sample, we use what's called a T-statistic rather than a Z-statistic. So what's really wrong with Z? Well, Z needs the population standard deviation. And usually we don't have that. Where T only needs the sample's deviation, which we typically write as S. So again, it comes down to the fact that we don't often have the information about a population. We only have information about a sample. So what does this do to our calculations? What does it do to our statistic? Well, let me explain. The T-statistic is still centered on the basic idea that sample means, sample proportions will appear normal or approximately normal in kind of a mound-shaped distribution. But the larger the sample size, the more normal it will appear. A smaller sample will mean it is less normal. So what you see on this chart, and this is table B, again, you should have a printout of what you're going to be given on the AP exam. You should see something here on the left called degrees of freedom. Degrees of freedom is a function of the sample size. And actually, to calculate degrees of freedom, we take the sample size and subtract 1. That's degrees of freedom. And the reason for that is, if you have a sample of 1, then that is your mean and there's no deviation. The minute you add another thing to your sample, you've created one chance for deviation. If you add 2 more, so you have a sample size of 3, you have 2 chances for deviation. So degrees of freedom is always the sample size minus that first original piece of data. Okay? When you have a super small sample size, you have this mound shape like this with large standard deviation. And the larger the sample size gets, the more it will appear normal. Okay? And in fact, if you look over at the table, you notice the bottom of the table is that kind of thing we've been looking at with the confidence intervals, right? You have your confidence and your Z stars that we've talked about. Well, you'll notice that scrolling up, those numbers get larger and larger and larger, you know, from our good old 95% that we always use. And the reason is, if the sample size is smaller, we know less about the group. So we allow for more variability. Or if you're thinking ahead to building our confidence interval, we allow more margin of error. In the next video, I want to talk about actually using this table for a calculation. In fact, most of the time you'll probably use your calculator for this. So the big things I want you to get out of this video are, why do we use T-Statistic? Because it's more likely that we had information about a sample rather than a population. Next, how does the T-Statistic differ from Z? It allows for a larger variability because we used a sample. Okay, if we knew the population, there is very little variability. We know a lot, but if we're only basing it on a sample, of course, more variability needs to be allowed. And as the sample size increases, we get closer and closer to the Z distribution. Now, the one thing I want to just address before we move on and you go to the next video is, people will always ask at this point in the course, well, why did we learn Z if we aren't going to use it? I mean, if that was unrealistic. There's not a great answer for that. The Z statistic, there are a lot of things that do appear normal. So it's not a bad calculation. But T is more realistic, especially for this kind of thing, where we're just saying a distribution of a sample mean. Okay? And in fact, the calculations are so similar. They're almost the exact same formula, just with a different chart. It's not bad to know the Z statistic because, of course, as I said, the calculations and the progression is almost the same.